A disk 8.03 centimeters in radius rotates at a constant rate of 1125 revolutions per minute about its central axis. So, this is a picture of the disk rotating. It doesn't really matter which direction it's going. And this is the radius. And then this little point would be the central axis. So this is just like, it's only balancing on this point. Like it's only, nothing else is holding up the disk. Okay. Part A, determine its angular speed in radians per second. This was probably the hardest question for me because I knew that everything else was based off of it. Like my answer, 118 radians per second, shows up in the rest of the questions. So I knew that it was going to be a big part of this, and I couldn't really figure it out. It was kind of annoying me. I knew that there was one definition of angular velocity that we use here, where it was just a version of that, but I forgot about the 2 pi frequency one, or I just don't remember really learning it. But either way, angular velocity is 2 times pi times the frequency, which is just this. It's the revolutions per minute. So 2 pi is just 2 pi, it's whatever. And then it's 1125 revolutions over 60 seconds in a minute, which is going to cancel to be 118 radians per second. And then here's my little angular velocity time graph. I know it stays constant because it's not asking for the speed at any given time. It's just asking for the speed, which means it's not changing. If it were changing, it would give me like, oh, give me the initial angular speed or the final angular speed, but it's not. It's just asking for the angular speed. Determine the tangential speed at a point 3.11 centimeters from its center. So it's like, okay, this thing is spinning, so it's going around. Now, okay, I'm going to draw a little, okay. So this is 3.11 centimeters. Now imagine it's going like in this, oh my god, I cannot draw a circle. It's going in this circle. How fast is it going then? Is the question. So the equation that we use is the one that I thought we should use for this one. It's tangential velocity is angular velocity times the radius, or the distance from the center. So this is 118 radians per second, which is again that really important number that we found in part A, and then it's 3.11 centimeters and not the 8.03 because we're looking at a certain point from the center. So later when we talk about like on the rim, that'll be something different. But since it's giving us this distance, then we know that it's there. So it ends up being 3.687 meters per second. Also, a big part of this was converting centimeters to meters. So this would be like 118 times 0.0311 centimeters. So that was also something that I messed up a couple of times before I realized like this needs to be in meters and this is centimeters. Part C, determine the radial acceleration of a point on the rim. I knew that I had to do this acceleration and not angular acceleration because like I said earlier, it's not angularly accelerating. The slope of this line is 0, even though that looks like it's a little crooked. It's supposed to be 0. So I knew that it had to be I knew that I was looking for like a centripetal acceleration. And instead of v squared divided by r, it's the angular velocity squared times the radius. So this is that essential 118 radians per second squared, and then it's this is supposed to be, I think, yeah, this is supposed to be 8.03. I don't know why it's something else, but okay, oopsies. So this, okay, yeah, this is our angular velocity, and then this is the distance from the rim, meaning like from here to here, it's just the radius, which is just 8.03, and then you get 1.11 kilometers per second squared, which I thought was so weird. And another thing that tripped me up, why is it in kilometers? There's no point for it. I know it's a big number, but we can handle the thousands. This is AP physics. Anyways, determine the total distance of a point on the rim in 2.01 seconds. So for this one, it was just, this one was also pretty straightforward. It's just like the arc is the radius times the angular position, and then we just said that angular position is just that, and then just worked from there with the pieces that we know. So it's the 8.03 centimeters because and that's just the distance from the center to the rim. This is that 118 radians per second, and this is the 2.01 seconds because it's what was given to us, and you get 19 meters, meaning that pretty much every 2 seconds you're going 19 meters, which seems crazy because this is like a fairly small circle, so it must be going really fast. But yeah, that's how I did this problem.